In this lesson, we introduce Kerckhoff principles and show how the key size is used to protect the secret. Augustin Kerckhoff is a Dutch cryptographer, published 2 articles in Journal of Military Science. One of the principles presented is all crypto algorithms must be public. Only the key are the secret. This principle is later well adopted and called Kerckhoff principles. Trying to keep the algorithm secret by following the security by obscurity principle will not work because 1, logistic issue, too much effort already invest, test, and install those new algorithms. If the software got stolen, or the design got stolen, and posted on the internet, it is lost forever. Second, publish the algorithms and let academics, researchers, cryptologists to break the system. If no one succeeded in 3 years, it must be pretty damn good. Kerckhoff principle is also related to principle of open design, where it advocates that security of a mechanism should not depend on the secrecy of its design or implementation. To decrypt a ciphertext, a cryptanalyst need to guess the key. If the key has 2 digits, there will be 100 possible combinations of keys. Using brute force approach, the cryptanalyst on average need to try 50 keys before able to decrypt. In another case, for key with 6 digits, there will be 10 to the power of 6, which equal to 1 million key. For the case of 64-bit key, there are 2 to the power of 64, which is equivalent to 1.84, 10 to the power of 19 keys. That's a lot. Assume one combination takes 1 nanosecond to test. It takes average of 1.84, 10 to the power of 10 divided by 2 seconds. That's about 585 divided by 2 years to break. This prevents your kid brother from recording your email. For 256-bit key, there are 2 to the power of 256, which equal to 1.16, 10 to the power of 77 keys. Assume the same 1 nanosecond to test. It will take average of 1.16, 10 to the power of 68 divided by 2 seconds, and 3.67, 10 to the power of 60 divided by 2 years to break. That will take a long, long time and will keep most of the governments at bay. In previous slide, we assumed it takes 1 nanosecond to perform the decrypt attempt. But in real world, how long will it really take to decrypt a file? Let's find out. And that also really depends on the size of the file and the machine we use. The faster machine, we should be able to decrypt as fast as we can. Here we compare the times for encrypting and decrypting short messages using the OpenSSL on Amazon AWS Cloud T2 micro instance, which is considered to be slower machine, and a Dell Optiplex 999 workstations in our lab, and a new MacBook Pro laptop, which I just purchased. on our Amazon AW instance in tilde/crypto directory, we have a software already installed. We use the following command to encrypt a file p.txt and save it in base64 format. The command is openSSL enc with the parameter -AES 256 CPC, which stands for AES encryption standard 256 bit chaining cyclic block chaining mode with a key value of CS591, and we use salt. We use EXED 64 base 64 kind of format. And here -A indicates the resulting ciphertext is encoded in base 64 format. We use the following command to decrypt p.enc. And here we use a -D to indicate we are doing decryptions. And using the same key CS591, same -A because we need to read in base 64 kind of format data. And the input file is p.enc. With the time prefix, we can actually measure the real time spent on each command. There is a time.pl and time2.pl in the same directory for compute 100 rounds of decrypt and encrypt with the right key or not, respectively. Here are the results on the three machines. That AWS Cloud T2.micro instance happened to perform the fastest with 0.286 seconds, followed by my new MacBook Pro laptop, and then my Dell workstation is the slowest one. The decrypt with the wrong keys spit out a little bit more messages, and therefore it is a bit slower than the one with the right key. Given the result from the previous slide, those three machines with OpenSSL command on short ciphertext, we now can calculate how long to brute force attack on AES encryption data. Let's use AWS T2 micro instance performance result on decrypting the wrong key, which is 2.93 milliseconds. It takes average of 5.4 10 to the power 66 years to break. That's a long time. Even with 100,000 times faster supercomputer, it will still take 5.4 10 to the power of 61 years. Of course, do not use key that is easy to be guessed by the hacker, such as 0, 1, even 1,000. They can try those beginning value or towards the end to the power of 256 minus 1, and maybe somewhere in the middle. Those values should be avoided. Most of the time, we use a randomly generated number with additional criteria to rule out easy to guess kind of keys.